So I'm going to go ahead and start by sharing my screen. Everybody hopefully saw at least that I sent you a link for a video to replace whatever happened Monday night. So again, you guys in the future, please let me know. I don't know what all y'all saw, or maybe it was working properly. But when I looked at the video, it seemed that I thought it was just my image that was changing because on my side of the screen, it was still showing everything I was writing. And from what I could tell, at least from the video that I watched, it seemed that a good fraction of the video had my talking, but it didn't. It froze up both my image of me as well as my image of my iPad, so y'all didn't even get to see the notes. The notes were all automatically saved to Google Docs, so you can still look at those notes. They would work fine with the audio portion of the video, but that's not a good way to do things. So I sent you out another video that should completely replace everything that you missed. And if I remember correctly, the video that I sent you a link to might have went a little further than what we covered. So what I'm doing today is acting as if we've already finished sections 10.1, 10.2, 10.3, and we're just jumping right into 10.4, which is where we started last time, or where we ended last time. So we're going to start today with some examples of calculating torque, and I'm going to explain a little bit more about torque and show you some other ways that will allow us to actually calculate it. So to do that, I'm going to go ahead and share our my iPad screen with you guys. Again, please speak up verbally and or chat if you see something go wrong like happened last time, because obviously that's sort of wasteful of your time, and I don't want to waste your time. It's wasteful of my time, but I get paid to be here. You guys are paying me to be here, so it's not fair to you by any stretch of the imagination. So please let me know. Uh, and not only that, please be as interactive as possible, because if the more you don't understand something and ask me a question, the better off you are at possibly understanding it. And not only that, if you don't understand it, there's a high probability that three or four other students don't understand it either. So here's the torque equals R cross F, and I taught you how to calculate a torque equals R cross F in that video as well as in the lecture the other night. But basically, whenever you take a cross product, you put the first vector in the cross product as its components as the second row of the matrix, and the second vector in the cross product you put as the third row in the matrix, and the first row of the matrix is just I hat, J hat, K hat. And then there's a long procedure in doing that. If you want to know more about how determinants were made up or anything like that, or if you want to learn some more tricks of how to calculate them, by all means, do a Google search or do a search on my YouTube channel for cross product or for determinant. I think determinant would be the better word, and you'll see. But one thing that I wanted to point out is there's the formula torque equals R cross F, which is the determinant of that matrix. I wanted you to realize that the vector R is what we call the lever arm, and that's a vector that extends from the center of rotation to the point of application of the force. Okay, so that's just a vector that goes this way. And normally, if it's like on a wrench or something like that, like I think I had this drawing earlier. Let me flip it over to this one. Yeah, so this drawing earlier, I drew that wrench and then I drew the force as if it's right here. But what I was actually pretending is the force is actually coming all the way down to here. So me drawing that is not technically accurate. If I did that, then the R vector would have to be like that, and then that would make it not exactly perpendicular. It'd be really close to perpendicular, so it'd be really good, but it's a really good approximation, but it's not perpendicular. So I would normally, when I draw a wrench like this, I'm going to assume that the force is acting all the way here to the midline, and that the lever arm vector is just along the midline. Don't worry about little discrepancies like that. But if you're actually doing a physical problem, you want to know accurately what's happening. So you do need the lever arm vector R. You need its arrow to touch the arrow tip of the force that you're doing in order for you to do it properly. So do keep that in mind in the future, but know that my drawings a lot of time are just rough estimates of what it's supposed to be, and that was a case in point. So I showed you how to expand on the I hat, and then if you got I hat, it'd be I hat times parentheses RYFZ minus RZFY. and then plus j hat, and then it'd be rzfx minus rxfz, and then it'd be plus k hat, and then that would be rxfy minus ryfx, and that's the result. But the other part of the cross product is that the magnitude of the cross product is r times f times the sine of theta. That's specifically the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. Whereas remember, the dot product was the same thing except it was a cosine. So I wanted to point out that there's actually two other ways of interpreting this that makes this even easier to calculate. Specifically, if we imagine R as broken up into a component that's perpendicular and a component that's parallel to F, then R would be this, that's R perp, and it would be there, and this would be R parallel, like that. And you see that R perp is actually equal to R times sine theta. So if you take this part and this part together, then that just becomes R perpendicular to F times F. However, if you try another way, if you imagine, for instance, breaking F up into a component parallel and a component perpendicular, then F would have F perpendicular to R would be F times the sine of theta, like that, and F parallel to R would be this vector over there. So you can see that in this case, the F and the sine theta makes F perp. So with this version, you end up getting R times F perp, where F is perpendicular, F perp is perpendicular to R. So that's the two ways you can interpret that magnitude formula, and then it's just a matter of using your right hand rule for the cross product. Remember, the cross product for the right hand rule has this index finger. I have them pointed like this, but this middle finger normally we start at 90 degrees, but it doesn't have to be 90 degrees. This is 90 degrees right here. But the vector, the second vector, can be anywhere all the way from 0 degrees all the way back to 180. The problem is, though, is when the two vectors are parallel, i.e. it's 0 degrees, or when the two vectors are anti-parallel, i.e. it's 180 degrees, then the cross product actually gives you 0. So if you want to use the right hand to find the direction of a vector, then you have to force yourself to only consider up to 180 point 179.999 degrees, all the way up to 0.00001 degrees. Okay, in that case, then the thumb points in the direction of the cross product. So again, first vector, second vector, and then the answer. So that's the way the right hand rule works. So with that in mind, let me just compute a cross product a couple different ways. And these are going to be very simple cross products, but I'm doing them with without a drawing in mind because I just want you to see the nuts and bolts of how to calculate it. So let's look at example. If R is equal to 1 I hat plus 2 J hat plus 3 K hat, and F is equal to 4 I hat plus 5 J hat plus 6 K hat. What is R cross F, which equals the torque? So that's a way of doing it. So I thought I'd show you real quick how to calculate the cross product. I'm going to do the determinant method, and then I'm going to do a couple other ways. So first off, determinant method. Okay, so with the determinant method, we're going to have R, well, torque is equal to R cross F, which equals the determinant of I hat j hat, k hat, and then 1, 2, 3, 4, 5, 6. So I expand upon the I hat, and the I hat happens to be the case where the location is row 1, column 1. And if you add the row number to the column number, you get 1 plus 1, that's 2. And if you raise -1 to the 2 power, that's a positive 1. So you don't have to do anything special. That was part of the whole rigmarole of how I came up with that formula. So when I do expand upon I hat, all I have left, because we're ignoring now that column and that row, so all I have left is this, and then the determinant is top left times bottom right minus top right times bottom left. So I'm going to be saying 2 times 6, 2 times 6 minus 3 times 5, like that. Now the next one is j hat, and j hat allows me to ignore this column and this row, so that leaves these two guys as the matrix. But j is the first row and the second column, and 1 plus 2 is 3, and when you raise -1 to the 3 power, you get -1. So the way I compensate for that is, instead of putting a negative in front of the j hat, I actually do the determinant backwards. So instead of going 1 times 6 minus 3 times 4, I go 3 times 4 minus 1 times 6. So in this case, I'm going to go 3 times 4 minus 1 times 6. And then for the k hat, that allows me to cover up this column and this row, so that leaves me this matrix. Of course, k is the first row and third column. 1 plus 3 is 4. -1 to the 4 power is positive 1. So I'm just going to do the regular matrix, which is where I do 1 times 5 minus 2 times 4. So now I'll say 1 times 5 minus 2 times 4. And that gives me, of course, 2 times Ugh. Excuse me, 2 times 6 is 12. 3 times 5 is 15. So 12 minus 15 is -3. So that's -3 I hat. 3 times 4 is 12. 1 times 6 is 6. 12 minus 6 is 6. So that'd be plus 6 j hat. And then 1 times 5 is 5. 2 times 4 is 8. 5 minus 8 is -3. So this would be -3 k hat. So that's what the actual torque is if those were my two vectors. Of course, it's really hard to even see what those two vectors mean because you have to graph them in 3 dimensions, but I thought it's important that you see what happens when all three components of both vectors are non-zero, so you'd see all the details. Another way you can do it is you can actually just use like the distributive property. So let me show you that real quick, and then that just takes a couple of ideas about that right hand rule. So we can determine the actual directions, but it's pretty straightforward. So torque is equal to R cross F. So we can just write R as 1 I hat plus 2 J hat plus 3 K hat crossed with 4 I hat plus 5 J hat plus 6 K hat, like that. Now, what do I mean by distributive property? I mean, I am going to take 1 hat or 1 I hat and cross it with 4 I hat, and then I'm going to cross it with 5 J hat, and then I'm going to cross it with 6 K hat. Then I'm going to do the same thing with 2 J hat, crossing it with a 4 I hat, then with a 5 J hat, and then with the 6 K hat. And then I am going to take the 3 K hat and cross it with 4 I hat, 5 J hat, and 6 K hat. So in doing it, this is the process that we go through. So first off, I've got 1 I hat crossed with 4 J hat, 4 I hat. Whenever you do a cross product, just like the dot product, it's what we call a linear operator. So that means I can pull all the numbers out to one side and just let the actual vectors operate on each other. So I'm taking the 1 and I'm taking the 4 and I'm pulling them out in front, and then I get I hat cross I hat. It's important that you keep the order of the cross product because I hat cross j hat is the opposite of j hat cross I hat, so they differ by a negative, and you'd get wrong answers if you didn't pay attention to that. So that's the first one. Now I've got to do the second one, which is 1 I hat cross 5 j hat. So that's going to be 1 times 5, and then it's I hat cross j hat, like that. And that's something we can work out. Now I'm going to do the third one, and the third one is 1 I hat and 6 k hat. So that's going to be 1 and 6, and then it's I hat cross k hat. Okay. Now I can do the second one, which is the 2j hat with the 4 I hat. So that's going to be 2 times 4, and that's j hat cross I hat. And then I can do, again, that's going to leave a little space there so I can put the answer. Now I can do 2j hat, 5j hat. So that's 2 times 5 times j hat cross j hat. And now I can do 2j hat cross 6k hat. So that's going to be plus 2 times 6. And this time it's j hat cross k hat. Again, something we can work out. And then finally, I've got to do the third one, which is 3k hat times 4 I hat. So that's 3 times 4 k hat cross I hat. And then 3 k hat cross 5 j hat. That's going to be 3 times 5. And then that's k hat cross j hat, like that. And then finally, the last one is 3k hat times 6k hat. So that's going to be 3 times 6 times k hat cross k hat. Now, I already told you that whenever the vectors are parallel or anti-parallel, so whenever A and B are parallel or A and B differ by 180, the sign, because the magnitude is R times F times the sine of theta, the sine of 0 and the sine of 180 are both 0. So all these I hat cross I hat, K hat cross the K hat, and J hat cross K hat is 0. So I hat cross I hat is 0. J hat cross J hat is 0, and K hat cross K hat is 0 automatically. So this brings me to another answer. So I can go ahead and say 1 times 5 is 5, but I hat cross J hat, I hat is this way, J hat is this way, and then K hat points in the direction of my thumb, which is the Z hat direction or the K hat direction. So I hat cross J hat is actually equal to K hat. So I get 5K hat, and that takes care of that one. I hat cross K hat, on the other hand, is, let me draw a coordinate system so you can think about it. Here's the X axis, here's the Y axis, and here's the Z axis. So that means this is I hat, this is J hat, and this is K hat. So if I do I hat cross K hat, that means the I hat points out of the page towards me and the K hat points up. And I see that my thumb now is pointing to the left. So I end up getting the negative J hat for this one. Okay. So in that case, I get negative 1 times 6, which is negative 6. Oops, I should probably keep writing that in purple. So negative 6 j hat. Now 2 times 4 is 8, and j hat cross I hat is the negative of I hat cross j hat. So we know j hat cross I hat is negative k hat. So this is going to be negative k hat for this one. So in this case, I'm going to say 2 times 4 is 8. So this gives me negative 8 k hat. The 2 times 5 j hat dot j hat's already 0. J hat cross k hat. I think you can see that j hat cross k hat, holding my hand like this, tells me that j hat cross k hat gives me the x hat or the I hat. So that's just going to be I hat in this case. Write this down. So that one's I hat. And 2 times 6 is 12. So this will be 12 I hat. And now 3 times 4 is 12. K hat cross I hat is K hat cross I hat is actually J hat. So this is J hat right here. So that's going to be plus 12 J hat. 3 times 5 is 15, but K hat cross J hat is actually negative I hat. So this one's negative I hat, which I will write with my red. Negative I hat for K hat cross J hat. So K hat cross J hat is negative I hat. So in this case, it's going to be negative 15 J hat. So now you can combine like terms, and you're going to see 5k hat minus 8k hat should be negative 3k hat. If I look at the i's, which is what I want first, I should have two i's in there. It looks like I've got. Oh, this last one was supposed to be an I hat, not a J hat. Stupid head. Yeah, that was negative I hat. So that should have been an I hat. Sorry about that. So now if I take 12 I hat minus 15 I hat, that should give me negative 3 I hat, which is what we got before. That takes care of this one and this one. The J hat is 12 hat minus 6 hat, so that'd be positive 6 J hat. That takes care of this one and this one. And now I've got 5k hat minus 8k hat. That would be negative 3 k hat, and I've taken care of all of them. And you see I got the exact same vector again. So that's the quick and dirty way of doing it, but you have to work out with the right hand ruler in your head. I just do it in my head, and there's some ways to help you with that, but just all you need to know in order to do that technique is you need I hat cross J hat is equal to K hat. Notice that is the first one, the X variable is the first, the Y variable is the second, and the K variable is Z, and that's the third. So it turns out if you make a cyclic permutation of 1, 2, 3, then you always get a positive. So for instance, if instead of I hat cross J hat, if I had J hat cross K hat, then that's 2, 3, and obviously, in order for it not to be 0, you have to have 1, 2, 3. You have to have the three different numbers because otherwise it's 1 and 1, which is I hat and J hat, or 2 and 2, which is J hat and J hat. 1 and 1 was I hat and I hat. 2 and 2 would be J hat and J hat. 3 and 3 would be K hat and K hat. All of those are parallel, so you're going to get 0. But as long as the three numbers are different, you're either going to get a negative or a positive for the answer. If it's a cyclic permutation, you're going to get a positive. So J hat cross K hat as a cyclic permutation is 2, 3. So that means the next one has to be 1. So that's a positive I hat. And then if you go ahead and say K hat cross I hat, which is 3, 1, then that's a 2, which is J hat. If, however, you do a non-cyclic permutation, for instance, you do J hat cross I hat, that's 2, 1, which is not a cyclic permutation of 1, 2, 3, then this gives you negative k hat, which would be negative 3. Similarly, if I switch these two, k hat cross j hat, that is 3, 2, which isn't a cyclic permutation, so I'm going to get a negative I hat because that's got to be the 1. And then finally, if I do j hat cross I hat, or excuse me, I hat cross k hat, you see that that is 1 with 3. That's not a cyclic permutation, and therefore this one's going to have to be 2, but it's going to be a negative, and that would mean j hat. So that's a quick and dirty way of realizing the pattern, but you can always not, you don't have to memorize that pattern or anything like that. You can just work it out in your head using the right hand rule. So any of that works. And then you just remember I hat cross I hat, or j hat cross j hat, or k hat cross k hat are all 0. And that allows you to come up with the same thing. So that's another way of calculating the cross product. If we wanted to do one more way, that's what I want to show you now. This one's kind of neat. This is sort of the origins of the definition of a determinant. So if I wanted to do a determinant of, let's say, I hat, j hat, k hat, 1, 2, 3, 4, 5, 6, just like the same one I had, what I can do is write the first column again, I hat 1, 4, and the second column again, which is j hat, oops, j hat 2, 5. Now the whole idea of the determinant came from using a number in each row and column for each multiplication problem, but only one number from each row and column. So if you multiply I hat times 2 times 6, then notice I'm using I hat, that's from the first row in the first column, 2 hat from the second row in the second column, and, or excuse me, 2, and then 6 from the third row in the third column. Notice none of those are two numbers from the same row or column. Then I do j times 3 times 4, and then I do k times 1 times 5. These numbers are added together. Then I subtract these numbers, which would be 4 times 2 times k, that's minus that, and then 5 times 3 times I, that's minus that, and then 6 times 1 times j, that's minus that. So that's really sort of the origin of the determinant, and it turned out to be super, super important. And I should say that I don't think you can do this for any dimensions higher than 3 by 3, if I remember correctly. You can check with a mathematician on that, but this is a nice and quick little way of thinking about it. Now, when I do that, notice what I get. 2 times 6 times I hat would be 12 I hat. And I'm adding to that the next red arrow. So that's 3 times 4 times j hat. That's 12 j hat. And now I'm adding the next red one, which is 1 times 5 times k hat. So that's 5 k hat. Now I'm going to be subtracting each of the green arrows. So minus 4 times 2 times k hat is 8 k hat. 5 times 3 times I hat is negative 15 I hat. And then 6 times 1 times j hat is negative 6 j hat. Now we can combine like terms, and we'll see 12 I hat minus 15 I hat is negative 3 I hat. That takes care of that one and this one. 12 j hat minus 6 j hat gives me positive 6 j hat. That takes care of this one and this one. And then 5k hat minus 8k hat gives me minus 3 k hat. And you see that we got the same number again. So that's more than enough ways of showing you how to do this determinant, and hopefully you've learned something and now have a bunch of fun ways. There's even more ways. I can introduce something called the Levy-Civita pseudotensor, and that's a quick and dirty way to get the individual components of a cross product, but that's neither here nor there. So we'll continue on now. Does anybody have any questions on that? All right. So we're going to look at example 10.7. And 10.7 says the bicep muscles exert a vertical force on the lower arm bent as shown in figure 10.15a and b. For each case, calculate the torque about the axis of rotation through the elbow joint, assuming the muscle is attached 5 centimeters from the elbow as shown. So we're basically saying that we're still going to have always the distance from the center of rotation of the elbow to the point of attachment for the bicep to part of the radius or ulna will be 5 centimeters away. And in two cases, we're doing one where the lower arm is at a 90-degree angle from the upper arm, and then the other one where the lower arm is at a 120-degree angle from the upper arm. So that's another way of looking at it. So let's work on that. I'm going to first draw the first one a little bit simpler and say this is the hand. What I have here is a force acting this way, and that force is 700 newtons. However, I have a a lever arm vector right here, R, that is equal to 5.0 centimeters, and that's going to be, if I treat this as if this is the x-axis and this is the y-axis, then that's going to be 5 centimeters I hat, and this force of 700 newtons would be 700 newtons J hat. But I'm not doing anything with vectors. I just wanted you to be see completely exactly what this scenario is, and this is part A, by the way. So now I'm going to calculate for part A. The torque is equal to, remember the magnitude is either R times F times the sine of theta, or R perpendicular times F, or F perpendicular times R. So R, F sine theta, or R perpendicular times F, or R times F perpendicular. If you see right here that F is in fact already perpendicular to the R, then you can see that I just need to do R times F. And in so doing, I'm going to get R, which is 0.050 meters. Notice I went ahead and converted it to meters, times F, which is 700 newtons, times the sine of 90 degrees. And the sine of 90, of course, is 1. That's why it just reduces to R times F. And in this case, I get 35.0 Newton meters is the torque. Now, that's the magnitude of the torque, and that's pretty much usually what you need. But in this case, you can see that I've got it aligned in a XY coordinate system. And if the XY coordinate system is right-handed, meaning this corresponds to X, the middle finger corresponds to Y, and the thumb corresponds to Z, then you'd see that in this case, Z has to stick out of the board. And for this case, R hat is in the I hat direction, or R is in the I hat direction, and F is in the J hat direction. So I'm literally calculating I hat cross J hat, which gives me K hat. So we'll say out of the page. That's the direction of the torque. Now, the other example was part B, and in that case, we had the upper arm pointing upward, and then we had the lower arm down at an angle of 30.0 degrees, like this. So there's your hand. And we still have 5 centimeters away. And I'll leave the vector off of this because I'm just writing the magnitude. So R is equal to 0.050 meters. And then I have, in addition to that, the force F, which is 700 newtons, is equal to F. So in this case, I can say torque is equal to R times F times the sine of theta. And that R is 0.050 meters. That F is 700 newtons. And then I'm doing the sine of, notice in this case, I can move the vectors so that they're tail to tail. And then the angle between the F and the R will actually be 120 degrees. So I can actually do that. Oops, it's supposed to be 120, not 126. 120 degrees like that. And when I compute that, that's going to be 35.0 Newton meters times the sine of 120 degrees. So when I do that calculation, 35 times sine 120 gives me 30.3 Newton meters equals the torque. And it's good to know that, in fact, this too is out of the page. Any questions on that? All right, let's look at example 10.8 now. Oops, happened again. Example 10.8. I'm going to draw this. Let's use this tool that I have to draw really good circles. There's one good circle. And I'm going to use this tool again to draw another good circle, but I want to sort of stress it out in the right size. There it is, almost perfect. I don't know why it wasn't more perfect, but there we are. Now let's delete that. Okay. This really just, I can't believe I'm even wasting my time with this, but I'm doing it anyways because evidently I can't help myself. Oh, that's not good. Ooh. It's really helpful that it all delays too, so that when I try to straighten it, it continues to move after I let it go. That's good enough. We're going to pretend like the centers of these circles are the same. But what I have here is a force acting on this one that's vertical, downward. And both of these forces, by the way, are 50 newtons. And I'm writing that extra zero just so you'll know that it's not 3 sig figs, it's actually 2. And the radius here, R A, and the radius to this one is RB. Oops, is RB. And technically that R, that B is supposed to be a capital B. So I'm going to write down RA and RB. So RA is equal to 30.0 centimeters. And yeah, and RA is 50, or excuse me, RB is 50.0 centimeters. And we know the forces are both, in each case, 50 newtons. But this other force is a little odd in that this other force is tilted upward at an angle of 30 degrees from the horizontal. Okay. And that is supposed to read 50 degrees, even though my thick pencil ended up making it all connected and look like crap. So there's 50.0 newtons like that. Okay, so if you'll notice, this 50.0 newton at 30 degrees tends to rotate the disc clockwise, and I often consider the clockwise direction the negative torque direction, whereas the vertical force on the RA is actually tending to rotate it counterclockwise, and I'd call that positive. And if I draw my X and Y axis like I had before, specifically this. I don't actually have to write the X and the Y here, but this is a common symbol that virtually all engineering and physics instructors allow you to use. But if you write that without the X and without the Y, everybody will understand that you're saying, hey, the positive X direction is to the right, the positive Y direction is up, and the positive torque direction is counterclockwise. Okay, so that's just like a note for sign convention. So if I want to calculate the total torque, what I'm going to do is the summation of the torques equals torque total is going to be the positive one, which is the 50 newtons, times the lever arm, which in the case of RA is 0.300 meters. And notice those two are technically the lever arm vector is perpendicular to the actual force vector. And because of that, all I have to do is R times F. Now, in the other case, the R vector is not perpendicular to it, but I can make it the component of F that happens to be perpendicular to the R vector. So I'm going to do it that way. And you can see that the component of F that is perpendicular has to be this one right here. So this is F perp, and F perp is 50.0 newtons times the cosine of 30 degrees. And of course, the cosine of 30 is equal to root 3 over 2, which is 0.866. So that's going to be 0.866. In this case, what I'm going to do is say minus, oops, still got to go with the purple. I'm doing minus because this is a clockwise rotation. I'm going to do 50, 0.500 meters. Never mind the fact that I'm putting in a different order. Now, what I'm doing is 50 newtons times the cosine of 30. So that gives me 43.3 newtons like that. And now I can do 50 times zero point 0.3 gives me 15 minus 50, or excuse me, minus zero point 0.5 times 43.3 gives me a total of minus 6.65. So this one turned out to be 15.0 Newton meters minus 21.65 Newton meters. And we really only had two sig figs, so it's not fair to say that. So this result is negative 6.65 Newton meters, and that 5 is not a sig fig. So that's my torque right there. Anybody have any questions on that one? Your book is calling this 6.7, and that's because they use two sig figs, and I've carried mine out to 3, but you see it does round to the appropriate value. Anybody have any questions on that? By the way, you might notice that your author writes meters times newtons, and that's fine too. And you can probably see why, because a newton meter is what we previously told you guys was a joule. And it's still equivalent to a joule, but no one uses the joule as a unit of torque. Everybody uses the newton meter or the meter newton as the unit of torque, and they never reduce it to a joule. So, the only time I'd ever see something like that is when maybe someone did it from a foreign language or something. But I even don't see that very often. It's normally very rare to see anybody do it that way. Anybody have any questions before we move on? It doesn't look like anything is getting locked up like last time. So the next thing we have to go on to is now that sort of covers our kinematics part. So I gave you all those equations for rotational motion, that were exactly the equivalent, like x equals 1/2 at squared plus v0t plus x0 has an analog as theta equals 1/2 alpha t squared plus omega 0t plus theta 0 and all that. That's the kinematics part. But in order for us to do the dynamics part, we need something equivalent to Newton's second law. Your book takes the time to do something like a pseudo derivation, if you will. And what he actually gets is this: the summation of the torques is equal to I times alpha. Okay. And this is for, he specifically comes up with this and tells you under what conditions it's valid. And this is a axis fixed, any axis fixed in an inertial reference frame. So this is for any rotational axis fixed in an inertial reference frame. In other words, we can't have an accelerating coordinate system that we're using. In other words, we can't have a coordinate system that's moving with the object and therefore is accelerating. If we did, then we couldn't use this equation for Newton's second law. However, he does a further derivation and gets the same equation with a little bit of a caveat, and its torque is equal to I times alpha, but it has parentheses around it, Cm and Cm. And what this means is if you restrict yourself to using that equation for an axis that goes through the center of mass of the object with a moment of inertia I, then you can be allowed something else. And this says for axis fixed in this case, axis fixed in direction, but may accelerate. So what we mean by that is, unlike the last one where we couldn't use an accelerating reference frame, we can use an accelerating reference frame here, but we're restricted to only reference axes that are fixed in direction. So, for instance, it could be rolling down an inclined plane, and long as the rotation axis didn't tilt this way or that way or this way or this way, then we could still use that coordinate system, and we just have to make sure we did our torque through the center of mass of the object that has a moment of inertia I, and that brings us what I hinted to earlier. I equals what we call the moment of inertia. And if you're talking about discrete objects, we have I is equal to the summation from I equals 1 to n of m sub I r sub I squared, where r sub I is the distance measured perpendicularly from the axis of rotation to the point at which the center of mass of m sub I is located. So in other words, we have to use the either point objects, or we have to figure out the center of mass of each of the objects that we're using, and then locate the point objects and figure out how far the center of mass of the object is from the rotational axis measured perpendicularly to that axis. So that's one version. But if it's non-discrete and we can pretend matter is continuous, then it becomes the integral of r squared dm, and I'm going to show you a couple of those as well. So that's how the moment of inertia works, and that's how Newton's second law works. So these guys are Newton's second law equivalents. So this is Newton's second for rotation. Now, there's also another version which he hasn't done yet, but I'll just write it over here. The summation of the torques is also equal to dl dt, and L is equal to R cross P. So that's just like the summation of forces is equal to dp dt, which I told you was the original version of Newton's second law. This is exactly analogous for rotation, where L is the angular momentum, and we'll learn about that in chapter 11. But with that being said, let's go ahead and work on example 10.9. So, example 10.9, it says two weights on a bar, different axes, different I. Two small weights of mass 5.0 kilograms and 4.0 kilograms are mounted 4.0 meters apart on a light rod whose mass can be ignored as shown in figure 1020. Calculate the moment of inertia moment of inertia of the system A when rotated about an axis halfway between the weights, and B when rotated out about an axis 0.50 meters to the left of the 0.5 or the 5.0 kilogram mass. So what we're asked for here is A, I through the center is question mark, and B, I through a parallel axis is equal to question mark. And now I'm going to draw the diagrams. So what we have here is I'll draw this as if it's a y-axis and this as if it's an x-axis. And what I'm going to have is right here at the 2.00 meters. Notice I'm going ahead and pretending like I have 3 sig figs instead of 2. Right here, I have a mass of 7.00 kilograms. And then right here at negative 2.00 meters, I have a mass of 5.00 kilograms. And my rotation axis is this one right here in the center. Okay, so that's part A. And therefore, I is equal to 5.00 kilograms. Now, the distance measured perpendicularly from the z-axis, or excuse me, from the y-axis, is in fact the x-coordinate. So that's going to be negative 2.00 meters, but it's going to be squared, so the negative is not going to matter. And then plus 7.00 kilograms times 2.00 meters squared. And this, of course, gives you 5 times 4, which is 20. So I get 20.0 kilograms meters squared. And the other one's going to give me 7 times 4, which is 28. So that gives me 28.0 kilograms meters squared. So I is equal to 48.0 kilograms meters squared equals IC. And I just subscripted C to remind us that was the calculation for going through the center. Now, in part B, they're asking it a little differently. So in this case, they're going to have the 5.00 kilograms right here. And then we're going to have our axis right here. And then we're going to have our 7.00 kilograms right here, so that this one is at 0.500 meters, and this one is at 4.500 meters, and our rotation axis is this guy right here. So this is I through a parallel axis. So I through a parallel axis in this case is 5.00 kilograms times 0. I just want to double check, make sure that was 0.50. Yeah, it was 0.50. So 0.500 meters squared, excuse me, plus 7.00 kilograms times 4.500 meters squared gives me 1.25 kilograms meters squared for 5 times 0.5 times 0.5 plus 7 times 4.5 times 4.5 gives me 141.75 kilograms meters squared. And in this case, we had 3 sig figs when we multiplied, so 1.25 is enough, and we go all the way up to that digit. The 0.7 is as far as we go on that one. So when I add 141.75 plus 1.25, that gives me 143 kilograms meters squared equals I through the parallel axis. Any questions on that one? All right, so that's how we calculate the discrete moment of inertia. Now I'm going to calculate a continuous moment of inertia for a rod, and I'm going to do it 2 different ways, and then I'm also going to show you the parallel axis theorem. So I'm going to do basically a bunch of different calculations here, and this is an example I'm making up, so I'm just going to call this example. Now, in the first case, I'm going to set up a coordinate system because I like setting up coordinate systems. It's not always necessary, but it always helps me think about what I'm doing. So in this case, I'm going to take a uniform rod. That would be like a broomstick where you've cut off the broom portion and you've even cut off the little hemisphere that's at the end of it that makes it rounded instead of flat. I want it to be completely uniform, so I'm cutting it off flat at there, just shy of the hemispheric top, and then I'm cutting it off perpendicular to the axis as well, right above all the attachments where the broom head sticks to the board, sticks to the rod. And what I'm going to say is this rod has a mass M and length L, and the mass is uniformly distributed. Remember, we showed you before that dm can equal lambda dl, or it can equal sigma dA, or it can equal rho dV. And uniform means that the lambda or the sigma or the rho is a constant. So in this case, I'm going to imagine this right here is a coordinate L over 2, and this back here is a coordinate negative L over 2. And I'm going to draw this little differential mass element right there. That quantity is dm, and that dm is going to be lambda times dl, but the dl happens to be acting along the x-axis, so we might as well call it lambda dx, because the thickness from here to here is dx, and the r is actually equal to the x coordinate. So with all that, I can go ahead and say I about the center of mass because I happen to be going through the center, and it's uniform. So the center is the geometric center. So the I about the center of the mass is equal to the integral r squared dm. And like I did before, the integrand is r squared. So, and part of it, of course, is dm. So I'm integrating r squared dm. I can't have dm differ much in r from one side to the other. That's why I had to make the differential length perpendicular to the x coordinate, and I had to make it super thin. In fact, the left hand side of the differential mass element is at x, and the right hand side of the differential mass element is at x plus dx. So they only differ by an infinitesimal amount. So I'm good to go on that. Now I have everything I need. I can go ahead and write that this is going to be the integral from x equals negative L over 2 to L over 2. The r is actually x squared, and the dm is actually lambda times dx. And I should say that lambda is just the mass divided by the length. That's the beauty of uniform things. You could just take the total mass and divide it by the total length in the case of lambda. In the case of sigma, you take the total mass divided by the total area. In the case of rho, you take the total mass divided by the total volume. And they're constant. So I can pull this lambda out in front, and I get the integral from negative L over 2 to L over 2 of x squared dx. And that, of course, gives me 1/3 lambda. Now I've got x cubed, but I've got to evaluate that at the point. So that's going to be L over 2 cubed minus negative L over 2 cubed. And the lambda is m over L, so I'm going to go ahead and put that in. So m over L. And now this becomes L cubed, oops, L cubed over 8 minus a negative becomes a positive L cubed over 8, because when you cube a negative, it becomes a negative, and a negative times a negative is a positive. So I get L cubed over 8 plus L cubed over 8, which is L cubed over 4. And therefore I have 1/12 M over L, L cubed. Ooh, just L cubed there, that's enough. And you can see that that gives me 1/12 ml squared is equal to I about the center of mass. So that's the moment of inertia if rotated about the center of mass. Now I'm going to calculate the moment of inertia about one end. So now I'm going to draw my axes slightly differently. There's my y-axis. Here's my x-axis. Now my rod, which does seem to look sort of thin vertically and thin in and out of the page compared to the width. So that's why we're treating it as a one-dimensional object. Only now it goes out to L instead of L over 2. And again, I'm going to say that this little distance from here to here is dx. This distance, which is r, is in fact x. And again, lambda is equal to m over L. Now I can compute I through a parallel axis is equal to the integral of r squared dm. We've already said that r is actually x, so I'm going to do the integral from 0 to L of x squared, and the dm is equal to lambda dx again. So that's going to be lambda dx. This gives me lambda times the integral from 0 to L of x squared dx, which equals, if I go ahead and replace lambda with m over L, I get m over L times 1/3 times, now I'm evaluating x cubed at L, that'll give me L cubed, minus x cubed at 0, that'll give me 0. So this is just 1/3 L cubed, which gives me 1/3 ML squared is equal to I about the parallel axis. So there's my moment of inertia about that parallel axis. Now I'm going to do the same thing using the parallel axis theorem. So the parallel axis theorem, I'm not going to cover the perpendicular axis theorem. That's easier in a more advanced class. But the parallel axis theorem says basically that the moment of inertia through a parallel axis is equal to the moment of inertia through the center of mass plus the mass times d squared, where d is the distance between the parallel axis and the center of mass rotational axis. So that's it. What we're going to do now is verify that we get 1/3 ml squared by using the center of mass moment of inertia. So IPA is equal to the moment of inertia about the center of mass. That's 1/12 ml squared plus m. Now the difference between the distance between the center of mass axis and the end axis is the distance of L over 2. So I'm going to put L over 2 and square that. Everybody see that that matches the formula for the parallel axis theorem that I was just writing down for you? Anybody have any questions on that? No problem, Anna. All right. So now when I look at this, I'm going to get 1/12 plus, if I square L, I get L squared over 4. So that's going to be 1/12 plus 1/4, both of which are times ML squared. And 1/4 is the same thing as 3/12. So 1/12 plus 3/12 equals 4/12. So that's 4/12 ML squared, which is 1/3 ML squared. And that's exactly the answer that we got before. So I'll check that, and that is I through the parallel axis. Anybody have any questions on that one? All right, so that is one of the more simple integral calculations that you can do. Of course, you can do other ones as well. I'm going to do a cylinder, rotation of a cylinder about the center of mass, and that'll be the last example that I do of calculating the moment of inertia. And this one I'm making up as well, so I'm just going to call this example, and I'll just draw it out again. Now, what I'm going to have here is an axis. Let's say this is our z-axis. Let's say this is our y-axis, and let's say coming out of the board or the screen is the x-axis. And what I'm going to do is draw a circle or a cylinder, but I'm trying to draw it in 3 dimensions, so I have to make it look oval or elliptical like that. And I'm trying to center it up, so hopefully that's pretty close. Looks like I got 3.5, 1, 2, 3. Yeah, that's not too bad. Okay. So it's a cylinder of mass m, radius r, and height h, has its mass uniformly distributed so that, well, that rho equals m over pi r squared h. What is I about an axis through its rotational, our center of mass, and rotational axis? In other words, an axis of symmetry. So you notice that if I put a axis right through the center of mass of the cylinder, then I can rotate that cylinder by any non-zero amount, and it doesn't have to be a whole like 90 degrees or anything like that. It's any degree, and the object will still look the same. So that axis is called the symmetry axis, and I just wrote it down as the rotational axis, which is not necessarily correct. It should be written as symmetry axis. But the same thing applies here. We still have to have I is equal to the integral of r squared dm. So our differential mass element can't have r differ significantly from one part of the differential mass element to the other. So because of that, the best uh, one to use for a differential mass element, at least if we're only restricting ourselves to single integrals, is basically a loop like this that then comes down to here like this, and this goes like that, and then inside of here goes up to there. So this little thing right here is dm is equal to rho dv. So the dV is going to be, if you looked at the top, you would call that dA, and that dA would be 2 pi r dr. But I need a volume, so I'm going to make that 2 pi r dr, which is the area of that little ring on top. I'm going to multiply that by h, and that's going to give it to me. So the radius is the actual r that we're using, and that's the radius from, polar coordinates or cylindrical coordinates. So this is going to be the integral from r equals 0 to big R of r squared times rho. We already have rho, but now it's going to be 2 pi r h times dr, because the thickness here is dr, and of course the height is h. And if you look at it, if you actually cut that shape out, it would look something like this, because it wouldn't be a perfect rectangle. So that's why I'm showing a little triangular in there. And then not only that, this would come down like this would come down like this, and that would be like that. This distance from here to here is 2 pi r, and then this distance is h. So you see the 2 pi r h is just the area of that side that's on the other side of the page, and then the dr is the thickness of that. So that gives you roughly it. Just trust me that it works, and you can look at my other videos and see me prove that it works. But either way, you're going to get the right answer, and that's one way you can prove that it works. So now I'm going to have pull out all of my constants, so I get a rho times 2 pi h times the integral of r cubed dr from 0 to big R. The integral of r cubed is 1/4 r to the fourth, so I'm going to get 1/4 rho 2 pi h times r to the fourth. Remember, we evaluate r to the fourth at r, and then we evaluate r to the fourth at 0, but the 0 one disappears. Now I'm also going to, first off, notice that this 2 cancels out with this 4 and leaves a 2. And that's going to give me a 1/2. And then the row, of course, is m over pi r squared h. And then I've still got a pi up here, and I've got a h up here, and I've got a r squared up here. So this pi is going to cancel out with this pi. This r squared is going to cancel out. Ooh, that's supposed to be an r to the fourth up there. I don't know why I wrote a 2. I think I already canceled it. Oops. So this is a 4. So that 4 is going to cancel out, leaving a 2 there. And this h is going to cancel out with this h. So that ultimately all I get is 1/2 mr squared. And if you look in table 1021, you'll see that that's exactly the right formula. So the moment of inertia of a cylinder rotated about an axis through its center is 1/2 mr squared. And as I said, see table 1021. Actually, it's called figure, so I should write that. Figure 1021. Okay, so that's enough for right now. We've gotten through section 10.4, which chapter 10 is really probably one of the longest chapters. So we're going to cover this some more. Uh, you can get a good fraction of chapter 10 done already. I haven't showed you examples using Newton's second law for rotation, so I've got to do that before you can really do it. So I'm pushing the homework back until at least Wednesday for right now. So even if I don't remember to do the date immediately, just know that you don't have to have it done until a Wednesday, or excuse me, till Tuesday night at 11:59 p.m. It would normally be Sunday, but I'm moving it to Tuesday night so that you can come back Wednesday and have it done. But I'm moving it to Wednesday. Keep an eye on your email. I'm still trying to work out that extra credit for face-to-face test 2, and I might send that, and I might even send you a video of maybe 1 or 2 problems that'll help you get started on chapter 10 homeworks more so than what I've already shown you. But have a good one, everybody. Thanks for coming. I'll wait for the last person to leave in case anybody has any questions. And you're free to go. Don't forget to chat me your first and last name if you haven't done so already.
Thank you. Have a great night.
Thank you, Michelle. Appreciate it. You too.
Thanks.
Thank you, Professor. Have a good weekend.
No problem. You have a good one too, Riley. Take care, sir.
Thank you.